Great. So just as a first introduction, this Thursday there is going to be a chemistry undergraduate research conference. There's some details. You can RSVP using this QR code. It's a good way, again, to explore the disciplines of other research going on in chemistry in and around the university. So I do encourage you to check it out. So last lecture, we talked about electrophilic aromatic substitution. We introduced aryl diazonium salts, how to prepare them and how to use them. And we started talking a little bit about their synthesis. And then finally, we introduced nucleophilic aromatic substitution. This is the last way to do functional group addition to a nucleophilic or to an aromatic system. And remember, there's a very specific pattern that's allowed. We need to have an electron withdrawing group in either the ortho or para position. So today we're going to talk about pericyclic reactions, introducing this concept of dienes and dienophiles, and then with a quick review of molecular orbital theory, which allows what we call the Diels-Alder reaction to occur. Now, you've already been introduced to pericyclic reactions. We saw these in lecture 10. This was the decarboxylation chemistry, and you notice the major thing that makes pericyclic reactions different is they go through this cyclic transition state. So that means we've got all the atoms that are involved, usually arranged in a 5 or 6 membered ring, and there's multiple arrows involved. So we actually have a total of 6 electrons that are involved in this transition state all in one point. And what we're doing is actually breaking and forming multiple sigma and pi bonds all in one single transition state. So this all happens in what we call a concerted reaction. Now there's a couple of very common types of pericyclic reactions. We're going to focus a lot on this one right here, what is known as cycloadditions. This is where we take 2 fragments and we actually make a ring as a result of that. So two unsaturated molecules come together to make a new cyclic product. If you notice, this has a similar sort of presentation as the decarboxylation. We have 6 electrons, and in this case it's 6 pi electrons from each of these double bonds, and we end up making a new pi bond and 2 new sigma bonds as a process of it. There's what's called sigmatropic rearrangements. This is where effectively a sigma bond is migrating across to the other end of a pi bonding system. So you notice here, very similar sort of setup. We still have a sort of 6-membered ring, but you notice here we have only 2 pi bonds and a sigma bond over here. We're still using 6 electrons, but what happens effectively is this sigma bond gets broken. We make a new sigma bond over here, and the double bonds shift over by 1 carbon. So we're sliding them over and over basically between 2. So what it ends up doing is moving this hydrogen to the other end of the pi system. And then there's what's called electrocyclic reactions, again forming a cycle or a ring. Here we take a system that has unsaturation, a polyene or a triene in this case. And then by heating it up, what we're doing is we're actually migrating the double bonds to create a new 6-membered ring where we've made this sigma bond right here. So the main one we're going to focus on for a little while is what's known as a cycloaddition. That's that kind of first case, as a Diels-Alder reaction. Now Diels-Alder reactions are very important. What we do is we call a 4+2 cycloaddition. That's referring to the number of atoms. So we have a 4-atom system, and we have a 2-atom system that ends up into this 6-membered ring. Specifically, a Diels-Alder reaction uses what we call a diene, so something where we have 2 double bonds, and a Dienophile. So this is it's usually just an alkene. Now notice we're using the same terminology we used before for things like electrophile and nucleophile. Now what we're saying is this is the molecule which will attack the diene fragment. That's why we have that naming convention along here. So here again, the 4n+2, we're talking about the pi electrons involved in the system. So there's these 2 here, and that's 4 pi electrons, and 2 electrons over on this fragment. Now, what's really important about this reaction, not only are we fusing together a 6-membered ring, we've made 2 new 6-membered or 2-member single bonds in this one transition state, but at the same time, what we can do is it actually allows us to set stereochemistry at all 4 of these centers. This is very useful. In fact, this is a very good way for us to actually bring complex molecules together in a very simple way. So I want to take a quick look at the thermodynamics of the Diels-Alder reaction. Now, if you remember back to Chem 123, what we have is a case where the Diels-Alder reaction, so forming this product here, at moderate temperatures, this is very product favored. So that's a case where it's spontaneously moving towards the product, or in other words, we could say the delta G at that low temperature is some negative number. However, at high temperatures, starting materials are now favored. We go back in this direction, we call that the retro Diels-Alder reaction. Now in that case, if it's spontaneous the other way, at high temperatures, this is a case where delta G is equal to a positive number. It's now favorable in the opposite direction. So if you go back to the relative equations for this, remember this equation is related where it's delta G is equal to delta H minus T delta S. And if you look at this system, we're taking 2 pi bonds, actually 3 pi bonds overall, and we're reducing it down just to a single. This is a case where the delta H is actually a negative number across this one. We're breaking up these stronger pi bonds. However, looking at the other part of this, we're taking 2 molecules and turning it only into a single molecule. That means that the delta S is going down. We're actually reducing the entropy of the system because we're taking 2 molecules and making a single one. So that's set up where as long as T is small, this is our major contributor to delta G. So delta G will be negative as long as this term here ends up being small because of a small t value. However, as t gets very, very large, this term dominates. Remember, we have a negative negative. That means that overall this is a positive term. So as t gets very large, that's where we get this delta G being a positive value. Now, in order for a Diels-Alder reaction to happen, the diene has to be in a very specific geometry. We call it the cissoid geometry. Now, conformation is where the 2 double bonds are cis relative to each other. So this is what we call this cissoid geometry. Now, there's 2 kinds of molecules. There are flexible molecules where you can have rotation about this backbone, in which case you have the cissoid geometry here, or what we call where these 2 are trans to each other. This is known as the transoid geometry. The Diels-Alder specifically needs this cissoid geometry in order for the reaction to occur. Now, there's other molecules where this cis geometry here is enforced or locked. So molecules like this readily undergo Diels-Alder reactions because they don't have to undergo some type of conformational change in order to get into the proper geometry. There's also other dienes like this one, which are conformationally locked, where they cannot undergo Diels-Alder reactions. There's no way to rotate it. It's always going to be this trans kind of form. So if you look through these, try to separate them out into molecules that might be allowed to rotate into cis or trans geometries. So here first, we have rotation here that's possible. We could redraw this in its cissoid conformation. It gets a little crowded, but that's possible. So this one's yes. That one can adopt a cissoid geometry, which means it can do a Diels-Alder reaction. It'll just be from this specific conformation. Over here, once again, we can rotate this bond. That would end up into our cis-type geometry. So we could end up looking like this. So yes, that one's possible as well. I'm going to go to this one next. I can technically rotate this, but if you try to draw this out, so into that cis geometry, I now have 2 tertiary butyl groups at that position. These very large groups here are going to bump into each other. That is not going to allow it to rotate just because of sterics at the end of this ring. This is a molecule. This is a molecule that can't adopt a cissoid geometry. So this one is no. This one here, it looks like it's locked where we have 2 of them on the same side, but take a quick note of that backbone. This, if I was going to look down at the top of this, I could actually draw this as a 6-membered ring shown like this with a bridging over top. Now, while these 2 are on the same side, they're actually pointing towards each other. We don't have this double bond, double bond type backbone. Here it is a double bond, single, single, double. So this, while it is cis, it will not undergo a Diels-Alder reaction. A diene has to have that pattern of a double bond, single, double, because it has to have extended conjugation through the 4 atoms that are involved. This is actually a 1, 2, 3, 4, 5 atom system from end to end, and also not a part of what we're going to do for Diels-Alder reactions. You can use it for photochemical things. It's actually going to be involved in other parts, but it is not a diene. So if you look at these ones, same question. Can these adopt a cissoid conformation in order to do a Diels-Alder reaction? So we could rotate here. That'll give us a cissoid geometry, so that's yes. This one's actually locked in the cissoid geometry. That's great. This one is locked in the trans geometry. That's no. This one here, even though it is sterically congested right here, it has that cissoid geometry, so in fact, yes, this one can undergo a Diels-Alder reaction. So the first part of our Diels-Alder reaction is to have what we call the diene. This is what we've been talking through. Remember, we're showing these all in their cissoid geometries, and these are very typically what we would use for Diels-Alder reactions. Notice that these are all typically electron-rich molecules. This is what we call the normal electron demand Diels-Alder reaction, where the diene is carrying some kind of an electron-rich component. So in each case here, I'm just going to highlight out the diene. We have this core fragment where we have donor groups from the alkyl groups. Remember, that's hyperconjugation helping to access that. Here, the diene is in this embedded backbone where we have lone pairs from something like this oxygen to help to donate into the ring. Very similar here, the diene is that kind of core. We've also got lone pairs and alkyl groups helping to donate in. And a molecule like this one, similar again, there's my diene, and I have a lone pair here. Now, yes, partial this is drawn off because of conjugation, but we have alkyl groups that are helping, and this will be delocalized into that ring to someone. Now, these are more locked geometries that are also possible. Remember, we talked about heteroatomic rings. These have a total of 6 electrons involved in a system. Even though that this is actually an aromatic system, having the 5-membered ring in this geometry does allow it to participate in Diels-Alder reactions. This molecule as well, this would be the diene system that's part of it here. Now, this is a very special molecule. We actually have something that looks like an extended system. Usually, this piece over here, the one that's kind of towards the outside or more accessible, is the one that would actually typically react once we come back to it. Now, while this one can undergo reactions, what you'll notice is this one here is actually not considered a diene, because if we were to sort of focus on that part of the ring, that's kind of the diene type geometry. That's what might be the cissoid fragment through here. The problem is we're going to be using this bond here and here to form my new ring. And if we did that, we're actually paying a price with aromaticity. So in fact, this does not involve, or we're not allowed to do Diels-Alder reactions with this one, because we'd have to basically break aromaticity around that point. A molecule like furan is the only one that we might be able to potentially use. Now, for now, we're going to look at what happens to the stereochemistry as we move to these substituted dienes. Now, I've tried to highlight this using this color coding. What you notice is that if we have 2 different groups, so one that's sticking outside the ring and one that's pushing into the ring here on one side, and likewise 2 on the other side, one into the ring, one out of the ring. When we do this reaction, what we end up with is a very specific geometry of our products. Every time this happens, the 2 outside groups end up cis to each other. The 2 interior groups end up cis to each other in this particular way. Since these 2 are anti to each other, they're also seen as anti here, and likewise, same geometry relationship over there. This is because when we do the cyclization, the molecule goes through a very rigid and very controlled transition state. So the relative position geometry you have of your starting material defines exactly where those molecules must go when you end up in your product. Now, I'm showing you here one geometry addition, so that's where This double bond is attacking or becoming our Diels-Alder reaction. I've showed you one molecule. The enantiomer is also possible, where you just have to flip both of these two centers. So all things, dashes become wedges, and we get the exact same mirror image of this molecule, but the relative presentations remain the same. The red R group and the blue R triple prime group are always on one side, and then these two are always on the other. Now let's go over to the diene. The diene is the other part of this reaction. Now while the Dienophile, the diene is typically a electron-rich system, the Dienophile, the other part of this reaction, is electron-poor. So what we have is the diene, the two carbons that are going to be adding into the system, and it's attached to a very strong electron withdrawing group. Likewise, these are the two carbons, and we have halogens, or CF3, or nitriles. So in all those cases, the core two carbons in the middle here are the ones that actually are going to be functionalized. Another very common one is if we have a diene or a dienophile, a simple two-carbon system here, where we have an sp2 carbonyl as our electron withdrawing group sitting out. Remember, this has a delta plus center and can act as a pi electron withdrawing system. Very other common dienophiles are also shown here. This is where we have these two carbons in the backbone with two electron withdrawing groups, or symmetric molecules like these, where we have the anhydride built in. Molecules like this with diesters, or our this is now an imide, right? You can also go to higher oxidation states. So this is where we can have a triple bond built in, where we have our electron withdrawing groups to the outside. So this is just a higher oxidation state, or similar in that sort of capacity. There's also one more very weird one, something we call benzyne. This is where it's effectively an aromatic ring, except there is a triple bond baked into here. Now this is weird. It's not quite a real pi bond. It's more like a diradical, but as a result of that, it's a very, very good dienophile, because we end up relieving that stress of having that that weird sort of electron pattern over here. Now, it is possible that if the only thing we have is something just like an aldehyde, aldehydes can undergo what are called hetero-Diels-Alder reactions, where it's actually an addition across the oxygen and carbon between these ones here. This is very rare and usually would only happen with aldehydes or small aldehyde fragments. And as we mentioned before, benzene, that carbon right there, these are not dienophiles. Once again, paying the price of aromaticity is usually too high, so breaking up benzene in order to do a reaction is not favorable. Now, something like benzyne is different, because we are actually using or burning one of those bonds in order to form benzene as a product, so it's actually driving towards aromaticity, and that's why it's allowed. So the stereochemistry we involve here is actually very specific. So if you look at the diene, remember we showed these guys before. The dienophile has has another sort of similar part in terms of the geometry. If we start off with the two chlorine groups trans, they end up in a trans relationship over here, where once again these two carbons are the two carbons that end up in our product. In our starting material, if those two on the dienophile are cis, then once again they end up in a cis relationship in our product, where these are the two carbons here and here that end up tracking through. So the biggest thing you can do when you're looking at your stereochemistry, look at the relative stereochemistry of the groups on your diene and your dienophile, and they will map over to the specific locations of where they get added to your product. So we spoke about how the relative geometry, so here these two groups are both on the outside, so they're going to end up on the same side as each other, and that's what you're seeing over here when you go to your product. Likewise, these two are on the same side, so they will be on the same side relative to each other. That's just talking about the relative geometry for the pieces on the dienophile and on the diene. Now, when the two parts come together, you're making two new sigma bonds, but they don't just approach each other. We're not sort of bringing the two fragments together in the same plane. What happens is the dienophile is either going to approach from the bottom or from the top of the diene. Remember, this is a flat plane, and we've got another flat plane here, so we're bringing these two flat pi systems together. And what I'm showing you in this specific one is a step-by-step transformation where you bring them together in the bottom face to make this trans-disubstituted product. Now, if you just look at piece by piece, step one, as we bring them together, we start forming these two new sigma bonds, and we start breaking all of our pi bonds. That's what we're showing in this representation. Then we get to a position where those bonds are now formed, and we've gone from an sp2 center at these two positions to an sp3 center. So it's going from planar to trigonal, or to tetrahedral, excuse me. So now that it's tetrahedral, we just have to flatten out the ring in order to make it look more like a normal cyclohexane. And now, while it's still in kind of a boat geometry here, what you can see is, imagine if you were viewing from this position. So this is your eye. If you're viewing in that location, now from the top, I actually have two hydrogens pointing up. That's why here and here, in the sort of wedge notation, those will be hydrogens. Dashes below that are these two over here. Similarly, these two are going to be wedge, and the two hydrogens down would be dash. So that's the relative geometry if we approached from the bottom that ends up turning into this geometry over here. Coming in from the top, we get the same relative geometry. So once again, these are on the same side as are these, but now notice we've got an inversion of the groups across this point. This is how we get the enantiomer of the product we showed you on the previous page. So as we approach in from the top, we start forming the bonds across these places. We end up forming those here and here, where we end up making our sp3 centers at these components up from our sp2 centers originally over here. So once again, we're going from planar to tetrahedral. And again, if I was going to view it from the top in this position here, if this is where I was looking, I'd see that these two hydrogens would be wedge and the R groups would be dash. And likewise, these ones, there's actually hydrogens pointing straight down. So these two are going to be wedge, and the hydrogens in this case are dash. So notice that this is a chiral product if these are not meso. Like, we need something that breaks the mirror plane across here. But if you look at the geometries we have here compared to this, that's how we end up with the two possible enantiomers of our molecule, either from the top or from the bottom face. So in this practice, try it later, we have the step-by-step guide of moving through this transformation and this ring flip. We're just showing them here. You can trace these out and sort of watch how this sort of goes, or try drawing it yourself. The other thing that really helps on this is to build a model kit to show you how those molecular transformations look and how we go from our planar geometries to our tetrahedral geometries at the centers where the new sigma bonds are being formed. Now, why we get this specific geometry or this enforcement in stereochemistry really comes down to molecular orbital theory. Remember, what we're doing here is we're starting with two molecules that have molecular orbitals. In particular, it's the pi orbitals, and it's reforming that molecular orbitals of our two starting materials to make a new molecular orbital of our product. Now, when we're doing this, bonding is happening by bringing together either non-bonding or anti-bonding orbitals in order to form these geometries. What we're doing is we're getting constructive interference between some atomic orbitals, which form a bonding relationship, but we're also going to be populating anti-bonding orbitals to break bonds. Now, because we're doing this, we're talking about the pi bonding system in particular. So if you look at something like our diene, in this case 1,3-butadiene, if we look only at the pi system is created by overlapping the 2p orbitals on each of these 4 carbons. So each of the 4 carbons is sp2 hybridized, which means they have 4p molecular or 4p orbitals atomically that get put together to make 4 molecular orbitals. That's the one most important thing about the molecular orbital theory, is the combination of atomic orbitals can be turned into molecular orbitals, and it's a summation. If we use 4 atomic orbitals that we're summing together, we will end up with 4 molecular orbitals. And the differences in what they look like comes down to differences in how we add or subtract either bonding or anti-bonding relationship based on the phases of the orbitals and the atomic orbitals that we're combining. So we can represent it in this way. So for 1,3-butadiene, we have 4 different molecular orbitals that are being combined together from these 4 possible atomic orbitals. So look at it almost like a combination theory. If we have these 4 p orbitals, the first way, the most strongly bonding way to bring them together is having all the bottom in one phase, all the top in another phase, which gives us a molecular orbital with this giant bond across all 4 and a bond across this one. Now, what we're saying is 4 atomic orbitals with this geometry can be combined to make this first molecular orbital, and because it's bonding all the way through, it's lowest in energy. It shows up here in the bottom. Next, we can add 2 in one phase and 2 in the other phase. So we have a single node in between those 2. So it's pretty heavily bonding on either side, but we have a little bit of an anti-bonding node between the 2. And as a result of that, it's higher in energy than our fully bonding one. And then we continue to do those combinations. Next up, we have 2 nodes, so that's 1 out of phase, 2 in phase, 1 out of phase. That gives us this double node. We still have bonding relationship in between, and that ends up in this third highest one. And then the highest molecular orbital is just every one of them is out of phase. We end up with almost no relationship between them. It's fully anti-bonding, or we end up with 3 nodes all between it. We call this one molecular orbital number 4. So that's just how we populate or create the shapes of our 4 possible molecular orbitals. Now remember, since we're bringing together 1, 2, 3, 4 atomic orbitals, each of them has 1 electron. So we have a total of 4 electrons that we can now populate into our 4 new molecular orbitals. So if we do that using Pauli exclusion principle, we're going to pair them up, 1 up, 1 down. So those are the first 2 electrons and the second 2 electrons, and then we're done. Since we only have 4 electrons from our 4 atomic orbitals that we're putting together, we can actually fully stack them into these molecular orbitals, where we've now have 2 paired bonding relationships in these lower 2 orbitals. Now, what it means is these higher 2 ones, where there's more non-bonding character, where there's more of these nodes, we have no electrons there, and thus no anti-bonding character is being populated. That's where we get the designation, where the highest occupied molecular orbital is this one here. The next up is the lowest unoccupied molecular orbital. This is where, if these are electron-rich, the electrons here will be participating with the as the nucleophile effectively. With respect to the Dienophile, we only have 2 centers, which means we have 2 p orbitals, only 2 of them. We bring them together, we have 2 atomic orbitals and 2 electrons is going to make 2 molecular orbitals. We bring these together. What you notice is now we've got the bonding molecular orbital, both in the same phase, makes a molecular orbital like you see here. This is our classic pi bond. And then we have the anti-bonding molecular orbital. This is where we put them together and they're out of phase, and we end up with a node in between the 2. So now that we have our 2 molecular orbitals and our 2 electrons, we pair them together, and once again we get the highest occupied molecular orbital, where that's the bonding relationship. It's our normal pi bond. And then we have the lowest unoccupied molecular orbital. This is an anti-bonding orbital for that particular one. So that now gives us the sort of general geometry of both the bonding and anti-bonding orbitals and their relative sort of pairing and shape. Now, as it turns out, when we do the Diels-Alder reaction, this is usually the highest occupied from the electron-rich Diene. So that's this one here, is usually paired up at a similar energy level as the lowest unoccupied molecular orbital of the electron-poor Dienophile. That's this one here. So effectively what we're doing is we're saying these 2 electrons here are most strongly interacting with the antibonding orbital of my Dienophile. That's kind of the pairwise way that we put it together. And the reason that that's important is take a look at the carbons. Like if I looked at this here, what I'm kind of trying to draw out is I have my 2 carbons from my Dienophile, and then I have my 1, 2, 3, 4 carbons from my Diene. If you take a look at the orbitals here and here, that corresponds to the orbital geometries at these 2 ends. Over here, these 2 are just these 2 paces here. Take a look at the orbital pairing. That is going to pair with this one, so they have the same phase, and this pairs with this one. That's partly why the orbital geometry matters. So having the specific geometry of our highest occupied molecular orbital gives us this out-of-phase relationship between these two ends, which matches the lowest unoccupied, or the antibonding orbital of my Dienophile. Energetically, that's why what we're doing here is electron-rich things tend to push energy levels up, and electron-poor things tend to pull energy levels down. So it's almost like what we did is we specifically dropped the LUMO to match the highest occupied molecular orbital so that they're on the same plane relative to each other. So what that looks like, kind of looks like cross like this. The highest occupied molecular orbital, as I mentioned before, the phases are opposite on those two ends. That's what we've shown you on the previous diagram. And the antibonding orbital, the LUMO of our Dienophile, once again, those two phases match here too. That's why we get this specific geometry approaching in this kind of from the top and bottom phase, where the two flat parts come together to make this geometry over here. It's because of this molecular orbital theory and how the geometry of the orbitals line up is why we get this approach to form the geometry in this one here. And it's also why the relative positioning of the groups that are attaching are enforced. It comes together in this concerted ring-forming reaction, so whatever geometry we have in those R groups is maintained all the way through to our product.